Hello. In this lecture, we're going to go through some very basics of probability distributions and the concepts related to error bars. We're going to start off with a very simple data set consisting of a single quantity measured for a single group or a single condition. For example, our condition might be population of male adults, and we might want to measure, say, heights. So from this population, we draw some measurements. We might choose some subjects at random and obtain these sorts of values. So these are just a collection of data values, and I've just plotted an x at the value associated with each data point. Now, these data points actually came from what's called a normal distribution, and we'll go over what that means in a second. So a very simple visualization we can do to sort of make sense of the data is to plot a histogram. And here I'm going to step through exactly what that means. On the y-axis here I have what's called frequency, which is just number of observations. So to construct a histogram, we're just going to bin the x-axis here, just the values that we have, into discrete bins, and we're going to put a bar whose height indicates the number of observations falling within that bin. For example, in this bin that is approximately between negative 2.4 and negative 2, we find 4 observations, and so that's why the bar is this high. And we do that for the remaining bins along the x-axis. So this visualization tells us something about the distribution of these data. We see that most values tend to be approximately around 0, maybe plus or minus 1. Now, in order to further summarize these data, we can compute some useful numbers. The first useful number is the mean, and the mean is simply computed as the sum of all the data points divided by the number of data points, and we'll go see the formula for that shortly. And if we compute the mean of these data, it comes out to be approximately 0, as you can see, and I've plotted a little tick mark there. So the mean tells us something about the central tendency of these data, and it's a useful summary of all of these data points. The next number that might be of use to us is the standard deviation. Here I've plotted plus or minus 1 standard deviation calculated from these data, and I've put a little tick mark here which indicates the mean plus 1 standard deviation, and the tick mark here which means the mean minus 1 standard deviation. The specific formula for standard deviation we'll go over in a second, but basically the standard deviation tells us something about the spread of the data. In other words, the fact that we tend to find points near the mean, but we also are very likely to find points above about 1 standard deviation and also below a standard deviation. So that's two useful quantities that summarize these collection of data points. And let's look at one more example where the data points fall from something that's not a normal distribution. Again, we will define what that means in a minute. So again, we have values on the x-axis. The scale is a little bit different, not that important for the sake of this example. And here are our data points. We've plotted an x at every single data point that we observe. Notice that by I already we can see that these data are a bit awkward. There's a big clump of data points here and also what seems to be a second clump here. And that gives us some indication that these data are not normal. The y-axis is frequency as before, and now we plot our histogram. So we immediately see that there's a large collection of data points near the bottom end, or approximately at 10. And we also see what we saw by I earlier, namely that there appears to be a little subpopulation at around 50 to 80. Now, if we compute the mean of these data, we get this value here, approximately 18. And the standard deviation for these data is visualized here. And for these data, the standard deviation is approximately 15. So the difference between this tick and this tick. Now you can see that neither the mean nor the standard deviation of these data is a great description of these data. So the mean of this data set is, as I said, around 18, but that's at odds with the data, since most of the data points are actually approximately 10 or below. So the mean is not a great representation of these data. Neither is the standard deviation. For example, the standard deviation might be interpreted to mean something like, oh, it's easy and likely to find data points that are, say, 1 standard deviation below the mean, but that would be approximately 0. But we know, looking at all the data, that at least for this sample, there are no data points even 1 standard deviation below. So there are alternative statistics or calculations we can make, and these fall under the term of non-parametric statistics, which essentially means that they make little assumptions about the form of the data. The mean and standard deviation, on the other hand, are what's called parametric statistics. They make certain assumptions about the form of the data and are accurate and reasonable only if those assumptions are true. So a non-parametric statistic for the central tendency, which is what the mean was trying to quantify, is the median. So the median, the definition of the median is the value at which, in this case approximately 9, the value at which half your data set lies smaller than that value and half your data set is larger than that value. So for this data set, the median is again approximately 9, and it appears to match by eye what we see in the histogram, that it's a good representation of the central tendency of these data. And for the spread, the non-parametric statistic that can be used is what's called the interquartile range, and that's calculated from the 25th and 75th percentiles here, which are given by these ticks here. Percentile is the concept we just described, namely the 25th percentile is the value below which 25% of the data set lie and above which 75% of the data lie, and then likewise for the 75th percentile, that's the value below which 75% of the data lie and above which 25% of the data lie. And so the median actually is just the 50th percentile. So as we can see, these summary of this set of data is much more reasonable than what is given by the mean and standard deviation. So let's briefly look at the equations for the mean and standard deviation. And one difference between parametric and non-parametric methods is that there may often be a simple formula or analytic way to derive parametric statistics, whereas there may not be a simple formula for non-parametric statistics. So here we're going to look at the parametric statistics we just described. So the mean of x, so this is just x stands for the data that we have, and we're just going to use this kind of functional notation. So the mean is often represented by x bar, so I'm just going to say the mean equals x bar, and it's given by, this is one element of the equation, so this is just a summation over the number of data points. So I is an index that ranges from 1, 2, 3, 4, dot, 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 up to n data points, and x sub I is the ith data point. So what this expression is saying is just the sum from 1 through n of our data points. So we're just summing all our data points, and then we divide by the number of data points. And so this simple formula tells us how to calculate the mean of a given set of data. Now for the standard deviation, we just represent that here. STD of x, our data, is equal to, here's the first part of our equation. We have, again, the ith data point here. And what we're going to do with this data point now is going to subtract the mean and square. So what this inner term here is quantifying is the deviation from the mean of the data set. Remember, x bar is what is the mean as obtained through this formula. So by quantifying the distance or the differential between the ith data point and the mean of all the data points, and then squaring gets rid of the sign. So both positive and negative deviations from the mean are counted as positive. So we're going to compute this squared deviation for each data point, and then we're going to sum across data points. And the rest of the equation is pretty straightforward. We are basically going to divide by the number of data points. There's a little correction term here, but let's not worry about that for now. And this outer square root is really just going to undo in some sense, the squaring operation. So intuitively, really, what the standard deviation is quantifying is something like the average deviation from the mean. And that makes a lot of sense, at least in terms of our example. As we see here, the standard deviation being this large tells us that about on average, any given data point is that far from the mean. But remember, in our earlier example, that it may give a misleading picture if applied to data that is not normal. For example, this data set, the standard deviation is computed as this much, but arguably that standard deviation is not a good representation for the spread of the data. And instead, we might use these non-parametric statistics. The interquartile range, which I forgot to define, is simply the difference between the 75th percentile and 25th percentile. Of course, and there's other terms that if you don't want a full range of that, you can divide by 2, and that gives what's called the semi-interquartile range. But anyway, these percentile-based statistics are truer to the data and a more accurate characterization of the spread observed in these data. Of course, there's this other mode out here, or this other bump that these simple summaries don't sufficiently capture. But if we want to capture the entire data set in just a couple summary numbers, we might want to use these types of summary statistics. Okay. We've been implicitly using some terms like distribution of the data, and now we should formally define what that is. And we're going to look at a specific type of probability distribution that puts specific constraints on the distribution of the data, and that's called the Gaussian distribution. So here on the x-axis, we just have the quantity we're concerned with. We just call it x here. And on the y-axis, we're going to plot p of x, which just stands for the likelihood or probability of x. This function, this red line here, is the Gaussian distribution. It has a specific mean and standard deviation, terms that we've already heard. In this case, the mean, which is just the center corresponding to the peak of this little bump, is given by mu, and it's equal to 0. And the standard deviation of this distribution, visualized in this fashion and using sigma to indicate the standard deviation, the sigma for this distribution is 1. When the mean is 0 and the standard deviation is 1, that Gaussian distribution is referred to as the normal distribution. So the Gaussian distribution is very useful, as you often will find quantities in the world when measured are Gaussian. Specifically, the central limit theorem tells us something about why we might expect that to be the case. Let's briefly look at the formula for the Gaussian distribution. So we're going to define a function that tells us how to compute p of x for any value x. So p of x is equal to, we have this component here. This is just x, whatever value we're concerned with, relative to the mean. We're going to subtract the mean from x, and that gives us sort of the deviation from the mean. And often Gaussian distributions might be computed for data that have different scale and different units. And so what we want to do is sort of normalize this deviation we observe by the standard deviation. So after this division by sigma, we now have some sort of normalized units. The normal distribution, as we're plotting this figure, is already normalized because the sigma is equal to 1. And so after this division operation, we have nice units. Now, both positive and negative deviations have equal effect on this distribution. As you can see, it's symmetric. The distribution goes down if you go above 0 and also goes down if you go below 0. And so we're going to use squaring to achieve that effect. Now we have a magnitude of the deviation, irrespective of the sign, and then we're going to exponentiate that. So all I've done is taken this e stands for a constant, that's approximately 2.71, and all we've done is taken e and raised it to the power. So here we have e to the negative 1/2 of the quantity that we just computed. And what that does is basically generates this sort of bell-shaped curve that we see here. Before the exponentiation, this quantity would just simply rise with the distance from x, and now we've sort of inverted that and made it a bell shape. The last bit for the formula for the Gaussian distribution is simply a normalization constant that goes in front here, and all that does is scales the height of this curve you see such that the area underneath the curve is equal to 1. And so that property, namely the integration under the curve for a probability distribution, always has to equal 1. And that corresponds to the fact that when we draw a random sample from this distribution, it's the total probability of all of the possible events is intuitively 1. Okay, moving on. We're going to get into the concept of error bars, and to understand that, we have to cover some basics of the process of sampling. So in this case, we're going to start with a population, and the population is just a term to refer to the, in some sense, space of possible measurements that we could obtain in some given experiment. So in this case, we're going to assume that our population is given by the normal distribution. So this describes some sort of idealized case where every measurement we draw is sampled from this distribution. So we've seen this already. X is just the quantity we're measuring, P of X is the likelihood, and we have the mean and standard deviation indicated by these little bar ticks here, and the mean for this particular case is 0, standard deviation 1. So when we draw a sample, we're just going to draw random points from this distribution. And here's an example. Suppose we draw a sample size of 10 from this population. So I've put arrows corresponding to each sample that was obtained. And given this sample of 10 numbers, we're going to compute the mean of that sample. And the idea is we want to quantify the central tendency of the data set we've observed. So after computing the mean, we're going to be concerned with the uncertainty on this mean. The idea is if you only see 10 subjects or 10 measurements, there's probably some uncertainty about the particular 10 samples that we chose. If we were to choose 10 more subjects randomly, we might observe a slightly different result. And that's what we're going to visualize on the right-hand side here. We're going to be looking at what's called the sampling distribution of the mean. So here's how that proceeds. The x-axis is the same, the quantity we're measuring, and we also have on the y-axis likelihood, but we're going to be looking at a very conceptually different distribution. Okay, for the sample we just drew, we can compute the mean of those 10 numbers, and for that case, for that sample, the mean turns out to be approximately -0.1 here. And I just plot an x here to indicate that that's what we observed. Now imagine we repeated this exact experiment many times. So we draw a fresh sample of 10 data points, compute the mean, and put them over here, and so on and so forth. And we repeat that many, many times. The distribution of those results will follow this shape here. So in this case, the distribution turns out also to be a Gaussian distribution, but notice the spread is much smaller than the population distribution. And this distribution is the sampling distribution of the mean, meaning that it shows us for this quantity, the mean of a randomly drawn sample of size 10, what is the distribution of results that we can expect to obtain over many, many experiments. Now, this distribution, the mean of this distribution, mu, is identical to our population mean. So this population had a mean of 0, and our sampling distribution also has a mean of 0, which makes intuitive sense. Basically, our random samples are equally likely to be above or below the mean, so on average, our samples will also have mean 0. Now, the spread of this sampling distribution, however, is smaller. The standard deviation of this distribution is given by sigma divided by square root of n. So sigma refers to the population standard deviation, and n refers to the number of data points we drew, in this case 10. So because of this division by square root of n, this standard deviation of the sampling distribution is guaranteed to be as same if n is 1 or smaller than the original population. And so this makes sense because intuitively, if we drew larger and larger samples, suppose we computed the mean of not just 10 data points, but the mean of 1,000 data points sampled from this distribution, we would expect this quantity to become very small, which corresponds to the fact that we would be much more certain in the mean that we observed from our sample of 1,000. So this spread, namely the spread in the sampling distribution, tells us something about the uncertainty of our experiment. And what we typically use error bars, or alternatively confidence intervals, to refer to that uncertainty. Now we're going to go through another example that has the exact same spirit as we just saw, but uses non-parametric statistics. Suppose we start with this data set. So x-axis has some value we're measuring, and we observe these data points. These data were drawn from a non-normal distribution, and you can kind of see that because you see sort of a clump here, and then the tail kind of drags out to the right-hand side for quite a long time, whereas the leftward direction only has a couple data points. Now, given this distribution, we could go through the exact same parametric statistics we just saw. However, the results may be misleading if these data are not normal. So instead, we're going to look at the results of bootstrapping these data. So bootstrapping refers to a procedure. It's a non-parametric procedure that is computationally intensive, but that can be used to quantify our uncertainty in some quantity we compute from these data. And recall the quantity median that we saw a couple slides ago. We might want to use the median to summarize these data, given that it looks somewhat not normal. So let's go through how we bootstrap the median and how we use the bootstrap to obtain quantify the uncertainty we would have in the median of these data. So the first step in bootstrapping is to draw a bootstrap sample from these data. And what that means is to draw a sample of size 20. Let's assume that the number of data points here, I don't know exactly how many I used, was 20, and we're going to draw 20 points from the data that we observed, and we're going to draw with replacement. So every time we choose a random data point and allow that data point to enter our sample, and we do this 20 times. I've indicated one bootstrap sample using arrows here, and so I have an arrow at every single data point that was chosen. Notice some data points are not chosen. And remember, some data points may be chosen more than once because we're drawing with replacement. Now, given a bootstrap sample, which is just another set of 20 numbers, we compute the median of those numbers, and we're going to plot that on the right-hand side here. So this will show our bootstrap distribution. We have the same value x-axis, and we have frequency on the y-axis. So given this one bootstrap sample we drew, we compute the median of that sample, and that might be approximately 2.9, as you see here. Now we're going to repeat this bootstrap sampling many, many times. Each time we draw 20 points with replacement, compute the median, and we plot that over on the right-hand side. And after repeating a sufficient number of experiments, we can do a histogram of our results. So this is analogous to what we saw a slide ago. It's essentially a empirically derived sampling distribution that we have just completed, and it tells us something about the certainty we can have in the median that we observed in our data set. For this distribution of results, we can use some quantities to summarize that. Let's use the median to summarize sort of the average, or in some sense average value observed in these bootstrap results. This median, recall, is just the value below which half the data points lie and above which half the data points lie. We can also use other percentiles. The median is just the 50th percentile, but let's use the 16th percentile, put that here, and then the 64th percentile, put that here, and the distance between those two percentiles is 68 percentiles, and so this gives us something like a 68% confidence interval, and it's analogous to the standard error confidence interval. So plus or minus one standard error tells us 68% of the sampling distribution. I forgot to mention that earlier. So what we've just covered is a Bootstrap method that allows us to quantify the uncertainty on the median of our data set, and we can plot that as error bars as shown here. To understand why bootstrapping works, here's a slide. So intuitively, what a bootstrap is doing is using the data as an empirical probability distribution. And so implicit in some bootstrapping procedure is the idea that for each data point, there's sort of a spike in the probability distribution that we're using. So each spike here corresponds to one of our data points, and we would have a bunch of spikes closely spaced together wherever the data are pretty dense. So this is a probability distribution that says that if we were to draw a random sample from this distribution, there's no probability of observing anything other than the points at which our data were collected. So everywhere where there's a spike, there's some likelihood that we might observe a data point. So this distribution looks a little weird, but let's look at some other closely related ideas. If we construct a histogram of our data, it would look like that. And this, in a sense, is also a probability distribution. If I just join the tops of the bars here, you see that the overall shape of this is pretty well behaved. It looks more or less unimodal with this big bump here, and the only odd part about this distribution is it has little discrete jumps. But other than that, it's a probability distribution that tells us, in some sense, where data are likely to be sampled from. The last one I will demonstrate here is one obtained using kernel density estimation, which is a non-parametric technique for essentially constructing histograms or smooth histograms of your data. So how that works is for each data point that we observed, let's just place a small little, in this case, Gaussian bump at each data point. So the first data point, the smallest data point, there would be this Gaussian bump shown here, and then every other data point we also place a little Gaussian bump. Now if we sum all of these probability distributions, and of course normalize by dividing by how many bumps there are so that our curves sum to 1, we observe something like this. This looks now like a nice probability distribution. Notice it is qualitatively very similar to the histogram. The main difference being that this one is much smoother than this one. Now, looking at these figures, we can see how bootstrapping works. So if you buy that the histogram is a probability distribution, then you will also buy that this one, obtained using kernel density smoothing, is also a valid probability distribution, and in some sense is nicer because you're not discretized from the histogram. But how we constructed this was very similar to what happens in bootstrapping. Really, the only difference between this distribution and this one is the fact that we added a tiny bit of noise in some sense at each data point. So if you take each of these spikes and posit that, well, we observed a data point there, but we probably also could have observed a data point, plus or minus a small amount around that data point. Well, as soon as we make that assumption, basically that there's some noise in some sense around each data point, we already obtain a nice looking probability distribution like this. So this shows us that bootstrapping is really just using the data as an estimate of the probability distribution of the population. Of course, we only observed 20 data points, so we don't really have access to the full population, but we will just use what data points we have observed and sample from those as if those define our probability distribution. And this diagram here is supposed to show us that doing so is not fundamentally different than doing something like taking a histogram of our data and using that as our surrogate distribution for the population. One last issue that may come up with histograms is the bin size, and this also applies to kernel density estimation, namely how big those little bumps should be when you construct a smooth histogram. If your bin size is too small, so here's an example that shows that what you might observe, notice that within any of these small bins, sometimes there's only one observation, 2, 3, and even the biggest bin only has 7 observations. And as you can sort of see visually, there's a lot of ups and downs in this distribution, and this would suggest that we've chosen too small of a bin size. Namely, this histogram will be highly unstable if we were to collect a new set of data and construct a histogram using this small bin size. Now, if you make your bin size too large, that risks obscuring some of the details in the distribution. For example, down here, it looks like there may be another mode or bump in the distribution, whereas if our bin sizes are too large, as shown in this example, that feature of the data is sort of obscured. The advantage, however, is that we have many observations in each bin. For example, this one is almost 25 observations, and this suggests that this kind of visualization of the data will be highly stable if we were to repeat our experiment. Now, somewhere in the middle, a middle bin size is probably right, depending on your definition of right. With this medium bin size, we see the overall structure of the data pretty well. So you see this kind of bump here and also another bump here. And we probably would find that this kind of characterization is reasonably stable across repeated measurements. If the goal of your analysis is just to make sense of your data, there's no harm in looking at your data in multiple bin sizes to kind of get a feel of the overall gist of your data.